Hello, welcome to today's video. In this video, we will talk about traditional thermal conductivity testing, commonly known as a TCT, or alternatively known as a thermal response test, or TRT. We will also discuss a new technology called a layered thermal conductivity test, or LTCT. This will enhance a traditional TCT and provide results with significantly more usable data. This advanced version is sometimes referred to as a DTRT, or distributed thermal response test. This video is presented by Andrews Hammock and Powel, a consulting engineering firm in Macon, Georgia. We are the principal investigators for DoD's Environmental Security Technology Certification Program, or ESTCP, in the field of underground thermal energy storage. We would like to thank ESTCP for funding the production of this video through their technology transfer programs. A TCT is a test used to determine the thermal properties of a geologic formation. The geology's thermal properties acquired via the TCT are needed to create a model used for both designing traditional ground loop heat exchangers, GHXs, or for an advanced form of underground thermal energy storage known as borehole thermal energy storage, or BETS. The analyzed results of a TCT allow an engineer to determine the thermal conductivity, thermal diffusivity, borehole thermal resistance, and the undisturbed deep earth temperature of the geologic formation. The thermal conductivity, also known as the K value, is the time rate of heat flow through a unit area and unit thickness of a material. In this video, we are using the flow of water to represent the flow of heat through the geology. A low water flow rate represents a formation with low thermal conductivity, or a formation with a low K value. The faster flow rate shown represents a high K value formation. Think of the flowing water as representing heat flow. The thermal diffusivity of a formation is related to the rate at which heat can spread or diffuse throughout the formation as it leaves the borehole. In this video, the cups represent varying degrees of thermal diffusivity. Thermal diffusivity, or alpha, attempts to quantify the rate of heat diffusion through a material by not only taking into account its thermal conductivity, the K value, but also its density and specific heat. As water, representing heat, flows, the smaller cups fill up quickly, so they represent high thermal diffusivity as they have less capacity to store water or heat. The larger cups represent a lower thermal diffusivity because they have more capacity to hold the water that represents the heat energy. The same is true for a geologic formation. The formation has a certain capacity to store heat. This capacity to store heat is related to its thermal diffusivity. As you can see, the flow rate of the water representing the heat flow is a separate property from its thermal diffusivity, which is represented by the size of the cup. The borehole thermal resistance, also known as BTR, is the measure of how much the borehole resists heat flow into the geologic formation. As the picture shows, borehole thermal resistance is the resistance from the U-tube heat exchanger pipes and grout that must be overcome before the heat reaches the formation. Heat must travel through the walls of the heat exchanger pipes, the grout inside the borehole, and the borehole boundary in order to reach the formation. A low BTR means that heat can more easily be transferred to a formation. The undisturbed deep earth temperature is the average of the underground temperature of the geologic formation as measured in the water inside the U-bend when the pump is off and friction heat from the drilling process has long since dissipated. To determine this value, a temperature probe is lowered to the bottom of the U-tube heat exchanger pipe, then the temperature is measured in 50-foot increments as the probe is brought back up to the surface. This data creates a plot of temperatures similar to the graph shown. The weighted average of all the data points is considered the undisturbed deep earth temperature. There are two different types of thermal conductivity test: a conventional TCT and a layered TCT. A layered TCT is an advanced version that uses distributed temperature sensing, or DTS fiber optic cable, placed in the U-bend to measure the temperature change as you move down the borehole. A conventional TCT can only determine the average K value along the entire depth of the borehole, as the fluid temperatures are only measured at the surface where the water enters and leaves the TCT rig. In contrast, the layered TCT can determine the K value for each of the strata along the length of the borehole. While an LTCT is sometimes more expensive to conduct, it provides data that can only be obtained by performing multiple conventional TCTs. For example, a single 500-foot deep borehole equipped with an LTCT testing apparatus can accurately measure the K value of each layer of the formation. In this way, a single 500-foot deep LTCT can report accurate overall K values for production boreholes that are 100, 200, 300, 400, or 500 feet deep for just the cost of a single LTCT and a single borehole. Often, the depth of the production boreholes is not known at the time of the field test, and accordingly, the LTCT result will be accurate and useful for any depth of the borehole eventually selected by the design engineer. In general, to run a TCT or LTCT on any formation, the following equipment is needed. A conventional TCT must have a borehole drilled and an HDPE U-bend inserted and grouted in place. The formation needs up to a week to cool to allow the heat generated by the drilling activities to dissipate. the supply of electrical power to operate the test, and a U-bend filled with water that has been allowed to equilibrate to the formation temperature. Even if permanent power is available, typically a properly sized generator is brought on site to ensure consistent voltage is provided throughout the test duration. Specialized testing equipment, commonly known in the industry as a TCT rig. A TCT rig pumps heated water through the borehole piping at a constant flow rate and with a constant power input to the heating elements. The TCT rig records the flow rate, entering and leaving water temperature, and the power input. This data is recorded at set intervals by data loggers and is stored to be retrieved and analyzed after the test. The picture shows an example of a TCT rig. A narrow cylindrical weight on a cable that is marked to show depth. This is known as a tag line. We use a tag line to measure the deep earth temperature and verify the U-bend depth. Data logging equipment that can measure and record flow rate, temperature entering and leaving the TCT rig, and the energy consumption of the electrical heating elements and the pump. Closed cell, half-inch thick or thicker pipe insulation that covers all HDPE pipe outside of the borehole. When running a TCT or LTCT, it is crucial that the sun has a minimal effect on the water temperature entering and leaving the U-bend, so the test apparatus must be well insulated. For a layered TCT test, these additional components are needed. All the materials used for a conventional TCT, as well as a distributed temperature sensing computer, commonly known as a DTS, and special fiber optic cable rated for submersion in water. Additionally, the data collected by the DTS requires more robust software to analyze the data since the DTS computer collects water temperature through the heat exchanger piping with a resolution of 2 meters. To perform a TCT or LTCT, the power supply must not fluctuate. Power provided by the utility company often fluctuates more than generators do, so it is recommended that a generator be used because it will typically supply more of a constant voltage to the TCT rig. First, the tag line should be lowered to the bottom of the U-bend to verify the depth. A weight must be attached to the tag line to ensure that the line goes all the way to the bottom of the U-bend. Next, a temperature data logger needs to be lowered to the bottom of the U-bend using the tag line. The data logger will measure the deep earth temperature of the ground as you raise it up. Pull the data logger up in 50-foot intervals to get a series of data points at different depths of the U-bend. The average of these data points is the undisturbed deep earth temperature of the formation. After the deep earth temperature is measured, the U-bend needs to be connected to the TCT rig. AH&P utilizes an H-pipe that can bypass the U-bend so that the air can be removed from the system quicker, but this arrangement is not mandatory. To connect the U-bend and the TCT rig, extra HDPE pipe may be needed. It is also recommended that a canopy tent be set up over the area to reduce the impact of solar radiation on the internal temperature of the TCT equipment. The TCT rig should be filled with water to the point that it can be seen in the standing water column/air separator. If using a bypass, make sure that the valves going to the U-bend are closed and the bypass is open. Turn the pump on and add water to the water column as the water level falls. The water level is falling because air is being removed from the system. Once the water level stops falling, close off the bypass and open the valves to the U-bend. If the water level falls, add more water until it is once again a constant level. Once the water level is constant, all the air has been removed from the system. This step is crucial because any air pockets in the line can damage the heating elements during the test. A flow meter can be installed on either the return or the supply side, but it is recommended that the flow meter be installed at a location where the maximum amount of straight pipe run upstream and downstream of the meter can be obtained. The entire length of the HDPE pipe needs to be insulated to reduce any heat loss outside of the U-bend. The 2019 ASHRAE handbook states the insulation needs to be a minimum of half-inch thick closed cell insulation, but thicker is preferred. Temperature sensors and data loggers should be installed in both the supply and return side of the TCT rig. The goal of the test is to measure the change in temperature while the water is inside the U-bend. It is recommended that at least 2 temperature sensors be installed in each side for redundancy and calibration verification. Electric heating elements serve to provide the energy input to the formation. The wattage utilized depends on the depth of the borehole. The ASHRAE guidelines for TCT state that the heating rate should be between 15 and 25 watts per foot of depth. Some wattage will be supplied to the water from the pump, which should also be taken into account. The standing water column should be capped off to reduce heat transfer. To conduct a layered TCT, these additional steps are needed. An LTCT test is an improvement to a conventional TCT, so all the steps for a conventional TCT and the following steps must be accomplished. Fiber optic cable needs to be inserted into the U-bend. To do this, one method is to install a T-fitting with an open port that serves as the entry point of the cable. The fiber optic cable is inserted into the U-bend with care to ensure the fiber optic cable is not bent or crimped, as it typically contains an internal stainless steel tube that serves to protect the glass fiber from water incursion or water pressure. Once the cable is lowered to the bottom of the U-bend, the T-fitting needs to be sealed to prevent any water from escaping during pumping operations. The other end of the fiber optic cable is then connected to the DTS computer. The DTS is programmed to measure and record the temperature of the water inside the heat exchanger piping along every 2 meters of the fiber optic cable. Both a TCT and an LTCT need to run for 36 to 48 hours to comply with ASHRAE protocols and to ensure the accuracy of the test. The data is then analyzed, and the thermal conductivity, thermal diffusivity, borehole thermal resistance, and the average deep earth temperature can be determined. This data can then be used to design a conventional underground GHX or BDIS system. Thank you for watching our video. If there are any questions, please contact us at the links provided in the description.